Hi guys, this is A2 Chemistry, Analytical Chemistry, and we are doing carbon 13 NMR. Question 1. Compound H is a primary amine which has 3 peaks in its carbon 13 NMR spectrum. An isomer of H is another primary amine J which also has 3 peaks in its carbon 13 NMR spectrum. Use this information to suggest the structure of J. So here we have three carbon environments, one of them being CH3 on both sides. This is one environment. We've got a CH2 in between on both sides, which is the second environment. And the third environment is a carbon directly in the center of the compound. So we need another compound, which is an amine, which is also going to give us three absorptions. That means three environments of carbon. So we can place in total, there are 5 carbons. So a carbon in the center with three CH3 groups on it. In this way, all the three CH3 groups will have the same environment. So they will correspond to one peak. The central carbon atom will correspond to the second peak. And since there are 5 carbons, the third carbon would be a CH2 group attached to the amine group, which would give us three separate peaks for the amine. So the peaks would be the central carbon atom, that is the first peak, the three CH3 groups as the second peak, and a third peak in the form of the CH2 group. So here we have got another amine which has three absorptions in its carbon 13 NMR spectrum. Question 2. State the number of peaks that would be seen in the carbon 13 NMR spectrum of CH3, CH2, CHCl, CH3. So here we've got a CH3 group attached to a CH2, that is one peak. Then we have a CH2 attached to a CHCl and a CH3 on both sides, that is the second environment. We've got a CHCl, which will be the third environment. And we've got a CH3 group attached to a CHCl, which would be the fourth environment for carbon. So in total, we would have 4 peaks for the given compound. Next, there are two isomers of this compound that have fewer peaks in the carbon 13 NMR spectra than the compound itself. Draw the structure of the isomers and state the number of peaks of each isomer. So we've got in total 4 carbon atoms. So in order to decrease the number of peaks from 4, we can place 3 CH3 groups attached to the same carbon atom. This would give us 2 different carbon environments. And since all 4 carbon atoms have been used up, the fourth position on the central carbon would be attached to a chlorine atom. So in total, we would have a single environment for the three CH3 groups and a separate environment for the central carbon atom. So in total, we would have 2 peaks for this compound. Now, we can remove one of the CH3 groups from the central carbon and place it between the central carbon and the Cl in order to increase the number of peaks from 2 to 3, but still have a lesser number of peaks than 4. So this would be CH3 attached to carbon attached to a CH3. Now this carbon would have a CH on it attached to CH2 and then finally Cl. So now here we have one environment of two CH3 groups, a second environment for the CH group, and a third environment for the CH2 group. So in total, 3 peaks for this compound would be observed, which is still less than the 4 peaks of the compound given in the question. Question 3. A sample of benzocaine shown below was analyzed by proton NMR and carbon 13 NMR spectroscopy. Predict the number of peaks that would be seen in the carbon 13 NMR spectrum. So we begin with one peak for the CH3 group here, another peak for the CH2 group here, a third peak for the C double bond O group here. Then we would have a fourth peak for the carbon on which the substitute group is attached. Then we would have a separate peak for the 2 carbon atoms on opposite side to the carbon atom coded in green. Then we would have another environment with the two carbon atoms adjacent to the purple carbons. Then we would have another environment in which we have the NH2 group attached. So in total, one, uh, two, three, four, five, six, and seven. So in total, we would have seven different environments containing carbon atoms. So the carbon 13 NMR spectrum of benzocaine would give us seven peaks. Question 4. Polyhydroxyamide is a fire-resistant polyamide which is formed from the two monomers F and G. Predict the number of peaks that will be seen in the carbon 13 NMR spectra of F and G. So looking at F first, we have one environment being the COOH group on both sides of benzene. Then the second environment would be the carbon atoms attached to the COOH group, and a third environment would be the remaining four carbon atoms on benzene. So in total, we would end up with three peaks for compound F. Now for compound G, we would have one environment with the NH2 attached to benzene. Then we would have a separate environment for the carbon atom on the top and a separate environment for the carbon atom on the bottom, because when the chain continues, the top carbon atom leads to another CH group, whereas the bottom carbon leads to a COH group. So that would change the uh, environment of carbon present. Next, we would have a fourth environment for the carbon atom next to the one on the top, and a fifth environment for the carbon atom with another NH2 attached to it, and finally a sixth environment for the carbon atom with the OH attached to it. So in total, we end up with one, two, three, four, five, and six different environments for carbon. Therefore, the number of peaks in the carbon 13 NMR spectrum of G would be six. Question 5. Compound W and Z were analyzed using carbon 13 NMR spectroscopy. Predict the number of peaks in the carbon 13 NMR spectrum of W and Z. So looking at W, we have got in total the number of environments. One would be common for both CH3. This is one environment. Then another environment for the two carbon atoms to which the CH3 group is attached. A third environment for the carbon atom between those two carbon atoms. A fourth environment for the carbon atoms that are next to the carbon with the CN attached to it. Then we would have another environment for the carbon to which the CN is attached. And finally, a sixth environment for the carbon atom of the CN group. So in total, we have one, two, three, four, five, and six different environments present in compound W. So we would end up with six different peaks in the carbon 13 NMR spectrum. Now looking at compound Z, there is one environment that is common for the three COOH groups. So that is one environment. Then the carbon atom attached to the COOH group on the benzene ring would be the second environment, and all of the remaining carbon atoms on benzene would give us the third environment. So in total, we end up with one, two, and three separate environments present on compound Z, giving us three separate peaks in the carbon 13 NMR spectrum of Z. Question 6. A sample of calcitriol is treated with an excess of hot concentrated acidified potassium manganate 7. There are three different carbon-containing products of this reaction. One of these products, X, is shown. Predict the number of peaks in the carbon-13 NMR spectrum of X. So, in order to predict the number of peaks, we would end up with a peak for this carbon atom. Then we've got two carbon atoms which have a similar environment adjacent to this one. So, this would be the second environment. The third environment would be the one the CH2 groups on both sides, and the fourth environment would be the C double bond O group at the bottom. So in total, we end up with 1, 2, 3, and 4 environments for the carbon atoms present in compound X. So the number of peaks in this carbon-13 NMR spectrum X would be 4 peaks. Next, for the carbon-13 NMR spectrum of X, state the expected chemical shift ranges of the peaks predicted in one and the number of peaks in each range. So we would have one peak in the range delta equals 25 to 50 ppm for the CH groups, or rather CH2 groups, and we would have three peaks in the range delta equals 190 to 220 ppm. This is the range for the carbonyl carbon. So this is for the 4 C double bond O groups. Although there are 4 C double bond O groups, but the number of environments is 3, so we would have 3 peaks. And there are 2 CH2 groups, but their environment is the same, so we would have 1 peak. So 1 peak in the range of 25 to 50 parts per million, and 3 peaks in the range of 190 to 220 parts per million for the 4 C double bond O groups present. Question 7. Molecules of cycloheptadiene C7H10 consist of a 7-membered ring with 2 carbon-carbon double bonds. Complete the skeletal formula of the 2 isomers of cycloheptadiene. So we need to have 2 different isomers. So an isomer can have a double bond present on 2 adjacent carbon atoms. That can be one isomer. And we can have another isomer with a double bond present on 2 carbon atoms with a carbon atom between them. So this will give us 2 separate isomers of cycloheptadiene. The isomers P and Q were analyzed using carbon-13 NMR spectroscopy. Predict the number of peaks that will be seen in the carbon-13 NMR spectrum of P and Q. So in P, we would end up with uh, an environment for these 2 carbon atoms, a separate environment for these 2 carbon atoms, a third environment for these 2 carbon atoms, and finally a fourth environment for this carbon atom. So in total, 4 environments are possible for structure P, giving us 4 peaks in the carbon-13 NMR spectrum. For structure Q, we end up with 1 environment for this carbon atom, 2 environments, or rather 1 environment for these 2 carbon atoms, a third environment for these 2 carbon atoms, and a fourth environment for the 2 carbon atoms at the base. So this structure also has 4 separate environments present, giving us 4 peaks in the carbon-13 NMR spectrum of structure Q as well. Question 8. Use of the data booklet to help you answer this question. The carbon-13 NMR spectrum of K was recorded. The structure of K is shown. State how many different carbon environments are present in K. So we start off with the carboxyl carbon. So this will be one environment. The carbon next to it would be the second environment. The carbon next to that would be the third environment. The carbon to which the benzene ring is attached to this group would be the fourth carbon atom. Now we would have two carbon atoms adjacent to that as the next environment, the two carbon atoms next to that as the next environment, and the single carbon atom in the exact opposite side where the substitute group was attached as the next environment. So in total, we have, let's count, one, two, three, four, five, six, and seven. Seven environments for structure K. Therefore, state how many different carbon environments are present K? Seven environments. Next, the chemical shift due to two of the carbon atoms X and Y present in K are given in the table. So X has a value of 130 and Y has a value of 170. So looking at the environments present, the value of X corresponds to the aromatic ring, which has a range of 110 to 160 nanometers, and Y has a value of 170, which corresponds to 160 to 185 parts per million for a carbonyl, or rather carboxyl carbon for carboxylic acid. So we end up with X being any one of the carbons on the benzene ring and Y being the COOH carbon atom. So here we have the two carbon atoms whose chemical values have been given in the table. So it says on the structure of K, circle and label two carbon atoms which would correspond to X and Y. So any one of the carbons on the benzene ring can be circled for X and the COOH carbon can be circled for Y. Question 9. Sample bottles of each of the isomers phenyl ethanoate and methyl benzoate have lost their labels and so have been named isomers A and B. The carbon-30 NMR spectrum of A and B contains the following peaks. The identity of the compound responsible for each spectrum can be deduced by studying the chemical shift of the peaks in the spectra. Use the data booklet to assign the correct peaks to the labeled carbon atoms in the structures of the isomers below. Write each value next to the relevant carbon atom and hence deduce the identity of each isomer. So if we look at both these isomers, the benzene ring is same in both of them, and so is the CH3 group. But the differentiating factor is the CH3 group itself, because that is the CH3 group in one of the isomers, the one on the left, it is attached to a C double bond O group. So when a CH3 group is attached to a C double bond O group, the range of the chemical shift values for this compound is 25 to 50. And if it is attached to an oxygen atom, the range for this peak would be 50 to 70. So in isomer A, we have a peak at 52, which corresponds to the CH3 group next to an oxygen atom, which is not present in phenyl ethanoate but is present in methyl benzoate. Here is the CH3 next to oxygen, because of which this peak is 52. Therefore, this isomer is isomer A. So phenyl ethanoate becomes isomer B. So the peak of CH3 next to C double bond O in isomer B is 26, which lies in the range of 25 to 50. Now, to complete the values for the other peaks, so now we've got a C double bond O, single bond O. This is the peak for the carboxylic group, and the peak for the carboxylic group lies in the range of 1 60 to 185. So in isomer A, the peak is at 167, and in isomer B, this peak is at 169. These two isomers are difficult to distinguish chemically. Describe a method of converting them to suitable products in step 1, which can then be tested in step 2. You should state the reagents and conditions for each step and any observations you would make. So we have one of the esters having a phenyl group in place of the alcohol and the other having a methyl group. So if we hydrolyze the esters, so we end up with a phenol molecule for phenyl methanoate, I guess, if that's the correct name. So phenyl ethanoate, and the other one is methyl benzoate. So we end up with benzoic acid and methanol. For phenyl ethanoate, we end up with phenol and ethanoic acid. So phenol can be tested by adding aqueous bromine, which would decolorize the aqueous bromine from brown to colorless. And when bromine substitutes onto phenol, we end up with the white precipitate. So overall observation would be going from brown to white precipitate, or brown color decolorizes and a white precipitate forms. So step 1 would be hydrolysis of the esters. So hydrolysis of the esters by heating with aqueous HCl, that would give us carboxylic acids and alcohol and phenol. And step 2, we add Br2 aqueous. So this results in the brown color decolorizes and a white precipitate forms. This white precipitate would be for 2,4,6 tribromophenol, and this would be possible with compound B. So you should state the reagents and conditions for each step, done, and any observations you would make, also done. Question 10. Ethane diol chloride. When ethane diol chloride is reacted with silver ethane diode in ethoxyethane at minus 30 degrees Celsius, an oxide of carbon L is formed. The molecule of L has no overall dipole and has molecular formula C4O6. The carbon 13 NMR spectrum of a solution of L in ethoxyethane is shown below. Okay, so we've got a peak in the range of 0 to 50, or 0 to this 10, this is at 15. So this peak is at 15. The other peak would be at 50, 60, and it is at 65. And the third peak would be 100, 110, 20, 30, 40, 50. This would be 160. So we have the chemical shift values for the three peaks in parts per million identified. Use the data booklet to state in the boxes below the chemical shift values for the peaks in the spectrum which are due to the carbon atoms in ethoxyethane. So if we have got CHC next to alkyl group, its range is 0 to 50. So for the CHC groups, the value for the chemical shift is 15 ppm. So CH2 next to oxygen would have a range of 50 to 70. So the peak at 65 corresponds to the CH2 next to oxygen. So we've identified two of the three peaks. So explain what the rest of the carbon 30 and NMR spectrum indicates about the structure of L. So the peak is at 160. It identifies that L has only a single carbon environment. That is why it only has a single peak present. So the structure of L is such that only a single environment for carbon is present in it. When pure L is reacted with an excess of CH3OH, a mixture of three compounds is formed. So we have got a compound with C2H2O4 called M, C3H4O4 called N, and C4H6O4 called O. So M is formed as one of the products when either N or O is heated with aqueous acid. So basically, hydrolysis of N and O results in the formation of M. So hydrolysis, so L reacting with alcohol produces M. That means M is supposed to be an ester. So what we have identified so far that M is an ester, and the ester has a chemical shift value of 162, which means all the carbon atoms are in the same environment. Okay. So N has three peaks. It has got 162, which is for the ester, which is not there in O. N and O has got a peak at 53 and 160. So 53 is basically CH3 next to oxygen. So these peaks correspond to CH3 next to oxygen. That means the remaining two peaks, which are 160, would correspond to, because hydrolysis taking place, would correspond to COOH groups. So 162 is for the ester group, 160 is for the carboxyl group, and 53 is for the methyl group next to oxygen. So that much has been identified. Now, suggest the structures of M, N, and O. So M contains two carbon atoms. So there are two carbon atoms present. And since it only has ester bonds present, or rather C2H2O4. Okay, so this is not the ester because M is formed as one of the products when either NO is heated with aqueous acid. So on hydrolysis, M is formed. So M is not the ester. So M is not the ester, M is the carboxylic acid, which means 162 is not ester, 162 is the carboxylic acid, which also means that 160 is the ester. So correcting the misunderstood chemical values, 160 stands for ester and 162 stands for the carboxylic acid. Okay, so coming back to structure of M, we've got two carbon atoms and both of them are carboxylic acid. So COOH and COOH. So this is oxalic acid or ethane 1,2-dioic acid. N has got one carboxylic group present on it. So this is the carboxylic acid group and it has got an ester group also. So C double bond O, single bond O, and it has got a CH3 next to the oxygen atom. In the structure of O, we've got two carbon atoms attached to each other, and it only has the ester group present and not the carboxyl group. So both these carbon atoms are forming esters, and both of them will be attached to a CH3 group with the oxygen next to it because we've got a peak for CH3 next to O present on it as well. So this way we've identified M, N, and O. Suggests a structure for L that fits all the data given in C and D. So L results in the formation of O. So we end up with two carbon atoms with two double bonded oxygen on it and a single bonded oxygen on it as well. It also gives us N. N has a carboxylic group and it also gives us M. Both are carboxyl group. And L has only a single peak at 165. So the only way all four carbon atoms in L have uh, a single environment is if on the other side of the single bond O, we end up with two more C double bond O groups. So in this way, we end up with the molecular formula C4, which is there, and O6, which are there as well. So this is the structure of L with four carbon atoms all present in a single environment.